We will continue our course video series with the design of logic circuits. To be frank, calling what we will do as design may be a bit exaggeration. We can better call it as synthesis of logic circuits, because what we shall obtain at the end will be logic circuit diagrams. Logic circuits can be categorized in two types. Combinational logic deals with circuits where the outputs depend on the present values of the inputs. You can also say that the outputs are logic combinations of the inputs. On the other hand, the outputs of sequential logic circuits depend not only on the present but also on the past inputs. Such circuits, which involve some sort of a memory, will be discussed in forthcoming videos. First of all, let us review the main steps in obtaining a circuit diagram. Of course, it starts with a problem statement. That is, we need a description of what the circuit is expected to accomplish. In many cases, this may be a verbal description. In any case, it should be possible to deduce from this statement how many inputs and outputs the circuit will have and how they are related. Using the problem statement, we can write a truth table which defines the output values for all possible combinations of the inputs. The output variables can then be simplified in terms of the input variables. This simplification is by no means limited to a reduction on a Carnot map, which can produce a simplification only in a standard form. In fact, one can consider various criteria for such a simplification. For example, one may aim at designing a circuit with minimum number of gates, minimum number of inputs to the gates, minimum propagation time from the inputs to the outputs, or minimum number of interconnections between the gates. You can also have restrictions on the types of the gates to be used in the circuit. Such a richness in the number of possible criteria and hence degrees of freedom in the design renders this step a trial-error process in most cases. Once the simplified Boolean expressions are obtained under these considerations, the circuit diagram that implements them can be drawn. Our first design exercise is on adders, that is, circuits that add binary digits. We can consider two types of them. A half adder is a circuit that performs addition of 2 bits, whereas a full adder is used to add 3 bits at once. Let us start with the half adder. Taking this definition of half adder as a problem statement, we can write the input-output relationship of a half adder as in this truth table. X and Y are the inputs, namely the bits to be added. S denotes the sum bit and C denotes the carry bit generated by the one-digit addition. So in adding 1 to 1, the 1-bit result, that is the sum bit, is 0, but the carry bit is set to 1. This carry may be used in the next significant bit addition of a multi-digit adder structure. The simplification step is quite easy here if one would like to obtain a circuit with least number of gates. S is a function of two minterms and can be written as x prime y or xy prime. This is nothing but an XOR operation between x and y. On the other hand, the carry bit is x and y. That means we can draw an implementation of a half adder as composed of 2 gates. Certainly, this is not the only possible implementation of an half adder. For example, the AND/OR implementation can be an alternative. To obtain an OR-AND implementation, we need to express the sum output as a product of sums. Since S is a product of the 0th and 3rd max terms of x and y, we can write it as x or y ANDed to x prime or y prime. That results in this implementation. Although OR AND implementation requires the same types and number of gates as the AND/OR implementation, it presents a more balanced distribution among these gate types. We can also write S prime as x prime y prime or xy and hence draw a 3-level implementation. This will reduce the number of interconnections as compared to other two-level realizations. You can draw this circuit as an AND-NOR implementation and reduce the number of levels to 2. Depending on your design requirements and constraints, one or the other of these realizations may turn out to be more preferable. In implementing an adder for multi-digit numbers, for adding each pair of digits, you actually need to add 3 digits at once, namely 2 digits of the numbers to be added and the third digit, which is the carry bit from the addition of the lesser significant digits. So let's design a circuit that can add 3 bits, that is a full adder. This is the truth table of a full adder. X, Y, and Z are the bits to be added. S is again the sum bit of the result and C is the carry bit. The carry bit will result in 1 whenever 2 or 3 of the bits added are 1. The sum bit S, on the other hand, results in 1 if the number of ones among X, Y, and Z are odd. The Carnot map of S reveals that it is not simplifiable as a sum of products. We can write S as a sum of 4 minterms. The carry bit C can be simplified as a sum of 3 products of 2 literals each, namely as XY or YZ or XZ. We can implement both outputs as AND/OR implementations. To obtain the circuit diagram for S, first generate X prime, Y prime, and Z prime, then use AND gates to implement all minterms of the function, and finally combine the outputs of the AND gates by a 4-input OR gate. Drawing the circuit for the carry bit is simpler. AND gates to generate the 2 literal terms and an OR gate that outputs C. There is also an alternative and heuristic way to approach the design of a full adder. Since the sum of 2 bits can be obtained by a half adder, it should be possible to implement a full adder by 2 half adders. We can first add X and Y by a half adder. Then we can add Z to the sum output of this first step by another half adder. The carry of this full addition may be due to either the addition of X and Y or the addition of Z to the sum of X and Y. To obtain the carry bit, we can OR the carry outputs of both half adders. To verify that this is in fact equivalent to the previous AND/OR implementations, let us replace the half adder blocks with the XOR and AND gate realizations. We see that the sum bit S is generated as X XOR Y XOR Z. We can expand first the XOR operation in the parentheses and then the other one by successive algebraic operations, that is, first applying the De Morgan's rule in the second term and using the distributive laws in both terms. We get the sum of same 4 minterms that appeared in the truth table of S. C, on the other hand, is written from the circuit diagram as XY or X XOR Y and Z. We can again expand X XOR Y as a sum of products. Then AND each term in the parentheses with Z. Here we OR the terms X, Y, Z to this expression by using the absorption theorem. Now, combining the second and fourth terms, as well as the third and fifth terms, we can reduce C to XY or YZ or XZ, namely the expression that followed via the truth table. Now we shall design subtractors. Just like the adders, the subtractors can be half or full subtractors, depending on the number of bits they process. A half subtractor performs subtraction of 1 bit from the other, while full subtractors subtract 2 bits from a third one. The truth table of half subtractor can be written as in this table, where D is the difference bit and B shows the borrow bit. Remember that subtraction is not commutative. This table shows the outputs for the one-bit operation as x minus y. Therefore, when x is 0 and y is 1, we have a borrow. From the truth table, it turns out that D is x prime y or xy prime, that is x XOR y. The borrow is given as x prime y. That means a half subtractor can be obtained by a NOT gate, an AND gate, and an XOR gate. Note that the sum output of an half adder and the difference output of an half subtractor are implemented in the same way, that is by XORing the input bits. What differs half subtractor from an half adder is only the NOT gate used in generating the borrow bit. Next, consider a full subtractor. Let us assume that x is the minuend, y and z are the subtrands. That is, we consider x minus y minus z. Then the truth table can be written in this form. For x equals 0, the difference output is 1 if one of the subtrands is 1. However, when x is 1, the difference is 1 if y and z both are equal to 0 or both are equal to 1. On the other hand, a borrow is necessary whenever the sum of the subtrands are larger than the minuend x. And in those cases, the output b will be 1. Similar to the half subtractor case, the difference output of a full subtractor turns out to be the same as the sum output of a full adder. The Carnot map does not offer any simplifications for a sum of products form. The borrow bit, on the other side, can be written as x prime y or yz or x prime z. That means if you replace x literal in the expression for the carry bit of a full adder with x prime, you get the borrow output of the full subtractor. Again, similar to the full adder case, you can design a full subtractor by using two half subtractors. You can first implement x minus y by a half subtractor. Then you can use another half subtractor to subtract z from the result of this subtraction. The borrow bit will be obtained by ORing the borrows of these two half subtractors. We can plug in the implementations of half subtractor instead of the boxes in this figure and write the logic expressions of D and B from this circuit diagram to verify that this configuration corresponds to what we obtained from the Carnot maps. But that I leave it to you as an exercise. We will continue design examples with code conversion. Let us design a logic circuit that converts a binary coded decimal, that is BCD symbol, to the corresponding XS3 symbol. In this truth table, the input side lists the BCD symbols of all decimal digits. The 4-bit output of the circuit will be the XS3 code of these digits. Remember that XS3 symbols are obtained by adding 3 to the corresponding BCD symbols. The outputs corresponding to the input combinations which do not represent a BCD symbol, that is 4-bit binary numbers between 1010 and 1111, can be taken as don't care conditions, because non-BCD combinations will never appear as inputs to this circuit. These don't care conditions are indicated by capital X's in the table. Let us start simplifying the output by Carnot maps. This is the map for W. Taking all don't care conditions as 1, W can be simplified as A or BD or BC. To simplify X, we'd better use the don't care conditions of the 10th, 11th, and 12th minterms as 1 and the others as 0, so that X can be written as B prime D or B prime C or B C prime D prime. The choice of values for the don't care conditions in the map of y is more obvious. We can arrange them so that all minterms in the columns corresponding to C prime, D prime, and CD are carried to the simplified expression. Lastly, by including the 10th, 12th, and 14th minterms among the minterms of the function, we can write z as equal to d prime. These maps give us the simplest forms of the outputs as they can be as sum of products. What else can we do if we aim for a circuit with a minimum number of gates? Let's have a closer look at these Boolean expressions. It seems that the term C or D can be factored out in W and X. We can write W as A or B ended with C or D. Also in X, we can factorize out C or D from the first two terms, as well as the third term. Then X can be written as B XOR C or D. Y, on the other hand, is expressed as an equivalence operation, that is C XNOR D. You see, considering all outputs together and using a bit of insight, they can be expressed with considerably smaller number of operations. Finally, we can draw the circuit diagram that implements the outputs as in these Boolean functions. Z is the simplest one. Next, Y is C XNOR D. To implement W and X, first generate the C or D term. This signal is XORed with B to yield X. It can be also used to obtain W by ANDing it with B and then ORing the result with A. So it takes 6 gates to build a BCD to XS3 converter. Next, consider a 3-bit gray code to binary converter. By this, we mean a circuit that can output successive binary numbers for adjacent symbols of gray code. We can write the truth table so that the inputs A, B, C are arranged in gray code order and the outputs X, Y, Z are 3-bit binary numbers from 0 up to 7. There is no need of a map to simplify X. Namely, X is seen from the truth table to be equal to A. On the other hand, the Carnot map for Y reveals that Y is equal to AB prime or A prime B. In other words, A XOR B. The map for Z seems to be irreducible. Well, yes, but only as a sum of products. However, writing it as the sum of minterms, we see that we can factor out C prime from the first and last terms, and what remains is simply A XOR B. Similarly, factoring out C in the second and third terms leaves us with A prime, B prime, or AB. In other words, the complement of A XOR B. Hence, Z is reduced to an XOR operation between A, B, and C. So these three expressions can be implemented only by 2 XOR gates. And guess what? The circuit will look like if the conversion would be on 4, 5, or more bits. Well, this ladder type structure would be preserved. That is, n-bit gray to binary conversion can be done by n-1 XOR gates. While mentioning XOR gates, let us discuss its properties in a bit more detail, since XOR function is indispensable in implementing circuits which accomplish valuable functions such as error detection and correction. Starting from the basics, XOR is a 2 minterm function of 2 variables, namely the first and second minterms. Also note that 0 is the identity element of XOR operation, whereas XORing a variable with 1 results in its complement. Further, X XOR X is 0 and X XOR X prime is 1. complementing any operand of an XOR operation complements the result. All these properties indicate that XOR function is an odd function. By this, we mean that if you XOR several bits together, the result is 1 if an odd number of these variables assume the value 1. In other words, the minterms of this n-variable XOR function are given by those minterm numbers which have an odd number of ones in their binary representation. Here we have the maps for 2-variable XOR, 3-variable XOR, and 4-variable XOR functions. Remember that adjacent cells in a Carnot map differ only in one literal. Therefore, if any cell contains a minterm of the XOR function, that is, if the minterm number has an odd number of ones, in all its neighbors the number of ones in the minterm numbers will be even. Therefore, in the Carnot maps of such multi-input XOR functions, minterms do not have any adjacent minterms by which they can be simplified to terms of less number of literals. XOR functions cannot be simplified beyond sum of minterms from a Carnot map. Similar properties can also be stated for XNOR function, which is a sum of the 0th and 3rd minterms. The identity element of XNOR is 1, and XNORing a literal with 0 is equivalent to complementing it. XNORing any variable with itself generates 1, whereas XNORing with the complement results in 0. As it is in the case for XOR, complementing an operand of an XNOR operation complements the result. It follows from these properties that a multivariable XNOR function can be represented as a sum of those minterms which are numbered in binary with an even number of zeros. The Carnot maps of multi-input XNOR operations look similar to those of XOR. In fact, if the total number of inputs is odd, even number of zeros means that the number of ones are odd. In this case, the maps of XOR and XNOR functions will be the same. For an even number of variables, they will be mutually complementary. In other words, for an odd number of bits, XORing or XNORing them will generate the same result, whereas if the total number of bits is even, they yield the complement of each other. It seems that one can test whether the number of ones in a bit sequence is even or odd by XOR operations. In other words, the even parity of a message of n bits is obtained by an n-input XOR gate. You can also check whether an even parity bit is correct or not by XORing the message bits and the parity bit all together. Therefore, we transmit the message with its parity to detect an odd number of errors at the receiver. This is how it will work. At the transmitter side, we use a parity generator, which is nothing but a multi-input XOR gate. For this example message, the even parity is generated as 1. The message is transmitted together with its parity bit. At the receiver, a parity checker determines if the message is consistent with its parity. This is done by XORing all bits including the parity. A 1 at the output of the parity checker indicates an error in the received message. In this case, the transmitter may be prompted to resend the message. For the correctly received bit sequence, the output at the parity checker is 0. Nevertheless, note that a double error may go undetected by the simple parity check mechanism. Actually, we might wish to not only to detect an error, but also to correct it without a retransmission. This may be achieved by using more than one parity bit in the message. Let us review one of the basic error correction methods, namely the Hamming code. Hamming code uses m additional bits to locate an error in an m-bit message. Since the erroneous bit location will be captured from the additional parity bits, and since the total number of bits in the message amounts to n plus m, the possible number of combinations of m bits, namely 2 to the m, needs to be larger than n plus m. You can also express this relation between n and m as m being larger than the logarithm on base 2 of n plus m. For example, for 20 bits of data, 5 more bits are required as 2 to the 5 is larger than 20 plus 5. Note that 4 additional bits would not be sufficient in this case, since 2 to the 4 is 16, which is less than 24. Or if you have a data sequence of 1000 bits, you will use 10 additional parity bits, since 2 to the 10 is larger than 1010. Let me continue explaining Hamming code on an example of 8 data bits. That means we will use 4 parity bits to decode this message. The key point in Hamming coding is the ordering of the data and parity bits. Here we denote the data bits with capital D and the parity bits with capital P. The parity bits occupy the locations that are numbered as powers of 2, namely 1, 2, 4, 8, and so on. We will denote also the parity bits by these numbers. Other locations belong to the data bits. Having fixed the places of parity bits, the next question is how they are computed. Well, each parity bit pi is obtained as the parity of data bits which have a 1 as the ith digit of their location number. To see more clearly what we mean by this, let us write the location numbers of the data bits in 4-bit binary form. To derive the parity bits, we can note the locations that have 1 in their 1s, 2s, 4s, or 8 digits. The least significant digits of 3, 5, 7, 9, and 11 are 1. So we write P1 as the parity, that is an XOR operation among X3, X5, X7, X9, and X11. Looking at the next significant digits of the data location numbers, we see a 1 for 3, 6, 7, 10, and 11. Therefore, P2 is equal to X3 XOR X6 XOR X7 XOR X10 XOR X11. Next, 1 appears at the 4th digit in the numbers 5, 6, 7, and 12. So P4 will be obtained by XORing X5, X6, X7, and X12. Finally, checking the most significant digits of the location numbers, we determine P8 as an XOR operation among X9, X10, X11, and X12. To exemplify the error correction operation, let us assume these values for the data bits we would like to transmit and compute the parity bits. P1 is an XOR of bits located as the 3rd, 5th, 7th, 9th, and 11th in the overall message. The result is 0 since effectively we XOR 2 1s and 3 zeros. Next, P2 will be XOR of 1, 0, 0, 1, 0, which is 0. There are 4 data bits to be XORed to obtain P4, and the result is 1. Finally, P8 too is found to be 1. Having completed the parity bits of message, it can now be transmitted to the receiver. To find out if the message arrived correctly, the receiver computes the parity bits in the same way as done by the transmitter and compares it to the received parity bits. This comparison can be done by bitwise XOR operations. For the received and computed parity, which do not match, these XOR operations will result in 1. Otherwise, they will be 0. The received parity bits are x8, x4, x2, and x1, namely 1, 1, 0, 0, respectively. The computed parities C4 to C1 are also 1, 1, 0, 0. XORing these bits pairwise results in a 0 of 4 bits. Therefore, we conclude that the received message is correct. To see how an error will be localized, let us rerun this transmission simulation. Again, the receiver side computes the parity bits C1, C2, C4, and C8 from the received message. The received parity bits are read from the message as again 1, 1, 0, 0. However, this time the computed parities are 1, 0, 0, 1. The bitwise XOR yields the result 0, 1, 0, 1. In other words, 5 in binary format, which indicates X5 has arrived erroneously. What if a parity bit is received erroneously? Would the error localization work as well? Let's try. That is, assume yet another transmission that is received as this bit sequence. Compute the parities C1, C2, C4, and C8 from this message. The received parity bits are 1, 1, 1, 0, whereas the computed parities are 1, 1, 0, 0. So the XOR operations generate a result of 0, 0, 1, 0, that is 2 in binary format. Therefore, the receiver detects the error in X2. Finally, we will draw the circuit diagram on the transmitter and receiver sides that can be used to localize an error. Once the data and parity bits are ordered in the message sequence, the transmitter uses a parity generator to produce the parity bits. This parity generator is a bank of XOR gates, which have the relevant data bits as their inputs. The data and parity bits are then transmitted in the predefined order. The receiver has the same parity generator. The parities are generated also at the receiver in the same way, and each computed parity is XORed with its corresponding received parity bit. The result obtained at the output of these XOR gates is called the syndrome. As the name suggests, this resulting binary number shows whether the message is healthy or not. If the syndrome is 0, the received message is correct. A non-zero syndrome indicates the number of the bit that is erroneous. In fact, this structure as is can only localize the error. In the forthcoming video, we will append some additional circuitry to what we have here so that the erroneous bit is corrected automatically. But for now, let us review our learning outcomes to close this part. Solving the exercises in your textbook, please check that you can implement adder and subtractor circuits in different forms, design code converters or other logic circuits that can accomplish a given objective using gate-level minimization techniques, obtain the check bits of an Hamming-coded message, locate and correct an error in a Hamming-coded message.